Hello and welcome back. Now in this lesson, we're going to dive deeper into common probability distributions, one of the most important topics in biostatistics. Now, probability distributions describe how data is spread and help us predict outcomes in medical and scientific research. Now in this lesson, we'll cover three key distributions: normal distribution and its properties, which is the famous bell curve used in many biomedical measurements; binomial, Poisson, and exponential distribution. And these are three essential distributions used in probability modeling. Now, by the end of this lesson, you'll understand how to identify and apply these distributions to real-world data. Okay, let's get started. So first, let's talk about normal distribution again. It's also known as the bell curve. The normal distribution is one of the most important probability distributions in biostatistics because many natural phenomena like height, blood pressure, IQ scores, cholesterol levels, follow this pattern. Now, the normal distribution has some key properties that make it useful in statistical analyses. Symmetrical shape is one of them. The normal distribution is perfectly symmetrical, meaning the left and the right have mirror images, basically. The mean, median, and mode are equal in normal distribution. The mean, again, is the average. The median, again, is the middle value, and the mode is the most frequent value. They're all the same. Then the 68, 95, and 99.7 rule, which is known as the empirical rule, which means that about 68% of values fall within one standard deviation from the mean, and about 95% fall within two standard deviations. Then about 99.7% of values fall within three standard deviations. As an example, the average blood pressure in a group of patients is 120 maybe, with a standard deviation of 10. Then that would mean that 68% of patients will have a blood pressure between 110 and 130. Now, the 95% of patients will be between 100 and 140, and then 99.7% within three standard deviations would be between 90 and 150. Now here's a graph to illustrate the normal distribution and the empirical rule of the 68, 95, and 99.7. It has, again, a symmetrical shape. If you cut it right down the middle, both of these sides would be symmetrical if you folded them in half. And this is a perfect bell shape, with the left and right sides being mirror images. Then the mean, median, and mode is represented by the black dashed line at the center, this dashed line. Now the empirical rule zones of 68% of all values fall between 110 and 130. This is plus or minus one standard deviation. So one standard deviation here, one standard deviation here from the mean, median, and mode. Now 95% of these values fall between 100 and 140. So this would be 95%. It includes two standard deviations on both sides. And then 99.7% falls between 90 and 150. So here you see 150 right here. 99.7 would include all of this here. So you can see 1, 2, 3 standard deviations from the mean, median, and mode. Now, if the average blood pressure is 120 with a standard deviation of 10, I mean 68% of patients will have blood pressure between 110 to 130, 95% of patients will fall between 100 to 140, and then 99.7% of patients are within the 90 to 150. Okay, now let's talk about the binomial and exponential distributions. So the binomial distribution is used when there are two possible outcomes, success or failure. As an example, did a patient recover from treatment? Yes or no? That is two possible outcomes. Did a test result come back positive or negative? That is two possible outcomes as well. Did a vaccine work or not? That's two possible outcomes. Now, a binomial distribution follows these conditions. A fixed number of trials, which would be n. A binomial distribution also has a condition that only two possible outcomes, success or failure, as I mentioned, exist. And then it must also have the same probability for each trial, which would be p again. The probability of success stays the same across trials. As an example, in a clinical trial, if a new drug has 70% success rate and we test it on 10 patients, the binomial distribution can predict how many patients will recover. Okay, next we have the Poisson distribution. Again, it's a French word. but this models the probability of rare events happening over time or space. This distribution is useful for counting events that occur randomly, but at a constant average rate, such as the number of patients arriving at an emergency room per hour, the number of car accidents in a city per day, maybe a number of calls a doctor office receives per minute, those types of things. Now, just as another example, if a hospital emergency room receives an average of 5 patients per hour, we can use the Poisson distribution to calculate the probability of getting 3 or 5 or 10 patients in the next hour. Now, finally, we have the exponential distribution, which describes the time between events in a process that happens randomly but at a constant rate. This is useful for modeling things like how long a patient is actually waiting before seeing a doctor, or the time between earthquakes within a region, or the time until maybe the next failure of a medical device. So as an example, if a hospital receives a new patient every 10 minutes, on average, the exponential distribution can model the probability that the next patient arrives in 5 minutes, 10 minutes, or 20 minutes. Today we covered normal distribution, which is the bell curve and its properties, the binomial distribution, which is the probability of success and failure outcomes, the Poisson distribution, which is modeling rare event occurrences, and the exponential distribution, which is predicting time between events. Probability distributions help us to analyze trends in biostatistics and make accurate predictions. Okay, thanks for watching, and we'll see you in the next video.